the same thing as there being a very short path from here to the goal. And walking around here is much, much longer. And uniform cost search tries everything. So it's going to try going through the wormhole and coming out the wormhole and getting there. Okay. Now we talked about breadth first search being a version of utility theory. Do you recall that? We're essentially saying every step you take has a cost. We're trying to minimize our costs by trying all these different things. What if some steps actually give you positive utility? For example, there's a donut right there. And that donut is worth +1, because everyone knows donuts are worth +1. Maybe it's an Oreo. Let's say it's an Oreo. Oreos give you +1. Now, going from here to there is a little bit more expensive, or a little bit cheaper than going like that. But that +1 reduces your cost, or maybe it's +10 or whatever it is. Will uniform cost search find the path that goes through the Oreo and gets to the goal if it's better, ultimately, than going straight to the goal? How many people say yeah? How many people say no? All right, we got one no. So somebody's taking a dissenting position. Let's suppose I put the Oreo right here. Now what's going to happen? It's going to think it's found the goal, and it's going to say, hey, the optimal path is to go like this. But in fact, we as humans solve this problem really well. We know the optimal path is to go like this. Because, I mean, it's not that far out of our way. Anyone would go that far for an Oreo, right? Wait, I think I'm confusing you by giving that Oreo a value of +1.
Yeah.
Okay, now we have given it the true value of an Oreo. Now you clearly agree with me that, of course, I don't know what unit this is. You know, maybe this is Zimbabwean currency or something where that is 1 penny. But it's pretty clear that now the right answer is something like that. I mean, it's still not to go like this, because that's dumb. But this is better than that because, hey, you get a +100,000 Oreo. And that's really nice.
Couldn't you tell the program just to continue until it can't move anymore, until everywhere's been visited?
You can. So this is another case for that backpatching step, right? What if even though you've found the goal, you keep on searching? Well, now we come back to that halting problem, and that's why I mentioned it a moment ago. What if you keep on searching until you get to right here? Well, what if the Oreo is just past that point, right? So you can never solve this problem of have I searched far enough? But assuming you've searched everywhere, or you've searched so far that you're just darn confident that you've searched far enough, then eventually you'll get to the point where you find that Oreo, and you'll keep trying stuff until you get back to the goal, and by that point you'll correct the path that you found and you'll backpatch it, and now the optimal path ends up being go backwards from here to the Oreo and then back to the start. Then you reverse that to get the true optimal path. So if I were to ask on a test, can uniform cost search solve the problem of positive utilities, where we're assuming every step takes negative utilities, but there might be some with positive utilities? This is the same thing as negative costs, right? Positive utility, negative cost, same thing. In general, when people study uniform cost search or breadth first search, they say that it assumes that all steps have negative or positive cost or negative utility. And they'll say it cannot handle this problem. But in truth, you can make it handle that problem by searching longer, as long as you search long enough. So what's the answer? Well, it depends on how I word the question, I guess. If you get it, then you're on the right track. Yeah?
I was going to say, what if they knew from the beginning that there's an Oreo on the map?
Ah, if you knew from the beginning there's an Oreo on the map, that's a really good way to put it. here's how I'd code it up. I'd have a flag that says, have I found the Oreo yet? And then once I did, I'd make sure that I continued to search long enough that I could also get from wherever the Oreo is to the goal. Because you need to make sure that you don't just find the Oreo, but also can search all the way to there so that it'll get patched up correctly. How would you do that? I guess if you searched at least twice as long as it took you to find the Oreo, would that guarantee you've got it? Something like that. Basically, there's various ways you could guarantee to get the optimal solution. But whenever you've got positive utilities, it really throws a wrench into uniform cost search.
Can you just do multiple uniform cost searches?
You could.
Uniform cost of the Oreo, uniform cost from the Oreo to the goal.
You could. I guess the question is, what if you didn't know there was an Oreo or where it was or something like that? Yeah. And now we get into all kinds of strain at gnat questions about how many goals and how many Oreos and where are the Oreos placed and how long are you allowed to search for. Do you stop as soon as you find the goal? Do you stop as soon as you find the third goal? Do you know a priori how many goals there are? Things like that. But mostly I just want you to have thought about in your head, do you understand why positive utilities kind of screw up the uniform cost search algorithm? Well, they do. Make sure you understand that.
Okay.
Next, I want to dive into an alternative search algorithm. Has anybody ever heard of something called A-star search? Anybody's heard of that? Okay. A-star search is the search algorithm of choice for a lot of problems. Let's see. Let me just compare it with uniform cost search. So here's uniform cost search. We're gonna let me do an example. Let's say there's a barrier here that looks like that. Let's say the barrier looks like that. Okay, so uniform cost search is going to keep growing these frontiers. God, it's kind of hard to draw with a mouse. It's going to grow these frontiers until they hit the barriers. It's going to keep on growing this way, and this way, and this way, this way, this way. Frontier's going to grow like that till it hits the goal. Do you agree that's what uniform cost search does? It is, that's what it does. Well, you as humans know that's kind of dumb, right? Wouldn't you rather it kind of searched like this? Oh yeah, I found the goal. That would be better, right?
Isn't that kind of implying you already know where the goal is?
That is implying that you already know where the goal is. The difference between A-star search and breadth-first search is, or I'm going to say the difference between A-star search and uniform cost search is one tiny little difference. The difference is that breadth-first or uniform cost search sorts its priority queue by cost. And A-star search sorts by cost plus estimate of how long it's going to take to get to the goal. Now, if you think about that for a minute, if you happen to be let's suppose you happen to be right here, and there's another spot that's right here, and they're both about the same distance from the start. According to uniform cost search, both of these points are equally good, right? Well, let's suppose that we also estimate the distance of the goal. So that's about 7. I think that's 7 distance units right there. How much is that? Maybe 19 distance units to the goal? Well, if we add 7 to this cost and we add 19 to this cost, then clearly that one's better. It gets bumped up in the priority queue, and so this one comes out first. What ends up happening is the frontier really does kind of reach towards the goal like that. Now, if you think about that for a minute, the frontier represents everywhere it's searched. So whereas uniform cost search is going to pretty much fill up the whole board, A-star search is going to find the goal after having only searched this kind of much smaller region. So A-star search is going to be a whole lot faster than uniform cost search. You see that? Okay. There's one really big rule with A-star search, and it's this: never overestimate the cost of getting to the goal. Why might that be? You always have to underestimate how far you are from the goal, because if you overestimate it, something really bad happens. Yeah, what happens is if you overestimate your cost of the goal, then you're going to get bumped to the very end of the priority queue, right? But in fact, that's not fair because you should have been explored, and so you're not going to get explored. And that basically means that it no longer guarantees to find the optimal solution. So A-star search is just like uniform cost search, except that, one, you have to know where the goal is, so you can estimate how long you have until you get there. Two, it loses all optimality if you overestimate how far you have to get to the goal. As long as you underestimate it, then it is guaranteed to be optimal, just like uniform cost search, and usually cost less. Okay. What kinds of problems would A-star search be well suited for?
Assignment 2.
Assignment 2. Actually, yeah, it would be well suited for assignment 2, in fact. And I'm making you do it in uniform cost search. Isn't that funny? Well, one thing you can do if you want to, and this would be really cool, is soup up your uniform cost search to turn it into A-star search. How hard is that going to be? Pretty trivial, I think.
And it's like 4 lines.
Yeah, it's an extra line of code. Do the experiment just because it's fun. I shouldn't even have to assign this to you. Let your curiosity drive. I know you're not going to do it. And I should assign this to you because I don't know what I was thinking by not doing it. I was just swamped with stuff. Next time I teach this class, I'm going to assign that. Just with an extra line of code, you can calculate the distance between where you are and the goal. You can multiply it by what? You need to guarantee you underestimate it. So how can you do that when there's this terrain map? Well, you can find the minimum value. I think it's something like 19 in the whole image. And you could multiply the distance by 19, because that's assuming the whole thing were a nice black path. That would be an underestimate. Part of the problem with A-star search is if the problem is at all interesting, it's impossible to get a good estimate of how far away your goal is. And if that happens, well, then A-star search doesn't really offer any benefits. And for that reason, I don't really like it. And for that reason, I don't really waste my time teaching it. However, if you work in the video game industry, A-star search is pretty much the de facto standard. So if you're going to if you're controlling some avatar and you click over here and your avatar walks this path to get to the trees to get over there, I guarantee you some variant of A-star search was performed in order to compute that path. Anyway, I'm out of time, so thanks for coming. If you still have questions on the assignment, use the forum. I think that's the best way to get these things done.